Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to power systems engineering, transmission line parameters. So far we have discussed about resistive, capacitive and inductive circuits, and also about the RLC circuit. So in this video we are going to discuss about another important aspect related to the transmission line, which is the conductors associated, which is the electric field due to conductors. Basic concepts which will be applicable to our discussion related to transmission line parameters. So electric field due to conductors. So first, the basic introduction, Coulomb's law. So it basically gives us an expression of electrostatic force of attraction or repulsion between two charges. For analysis purposes, we'll consider point charges which are separated by some distance. So let us say we have two charges, okay, Q1 and Q2. Their magnitudes can be different, they can be the same, whatever it is, they are separated by a small distance r. Here there are two positive charges, so there will be a force of repulsion. If one is positive, other is negative, there will be force of attraction. If both are negative, again repulsion. So they are separated by a distance r, so the electrostatic force of repulsion will be given by 1 by 4 pi epsilon 0, product of the two charges directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. So this becomes the Coulombic force 1 by 4 pi epsilon 0 q1 q2 by r square. If it is in air or free space, and if it is in any other medium, then in that case it will be 1 by 4 pi epsilon 0 epsilon r, which is the relative permittivity or the dielectric constant of the medium. Epsilon 0 is the absolute permittivity of free space or air. 1 by 4 pi epsilon 0 epsilon r q1 q2 by r square. This. So a very this is the general sense. Suppose we keep the same thing and we consider the two charges. One of them is the source charge and another one is the test charge. The source charge is responsible for the production of the Coulombic force on the test charge, and as a result of that there will be an electric field. So here the concept of electric field comes. So the electric field intensity or the electric field strength at any point is given by the force experienced by a unit positive test charge placed at that point. So here the force produced due to this charge, bigger charge Qs, which is called as the source charge at this point, will be Qs Qt 1 by 4 pi epsilon 0 Qs Qt by r square, same as Coulomb's law. But if we want to determine the electric field at this point, then simply we will divide this whole Coulombic force by the test charge Qt. Similarly, if we reverse this, suppose we want to determine the electric field at this point, then in that case this Qs becomes the test charge and it will be F by Qs. Okay, that is the thing. Coulombic force divided by the test charge placed at that point where we want to determine the electric field, that is called as the strength of the electric field or electric field intensity at that point. Force by charge, that gives us electric field strength at that particular point. Okay, then another important thing is electric potential as line integration of electrical field. Okay, electric potential as line integration of electric field. So in this case what we have to do, so let us say we have an electric field represented by the electric field lines. Okay. Suppose there are 2 points we pick, okay, VB here and A. The potential here will be VB and the potential here will be VA. And suppose we have to move a positive test charge from A to B. So we have to do work against the electric field, because this electric field will try to move it in this direction, and we have to do work against the electric field to move it from point A to point B. So in that case, the potential difference between these 2 points, VB minus VA, is called as the negative line integration of the electrostatic field. Okay, here we are not going into the derivation, simply I am only pinpointing those things which will be required for our discussion in transmission line parameters and the conductors associated with the transmission line. For detailed analysis, we will go for electricity and magnetism. In that playlist, we will discuss all these things in detail. Okay, unnecessarily why to extend this discussion. Okay, so this is electric potential as line integration of electric field. Then the electric field due to various types of conductors. So first, electric field due to a circular ring. So here we have a circular ring of radius r, and we want to determine the electric field at a point P, which is at a distance x away from it. So here this A, which is the distance from one small element dl. So here what the thing is, that we have to divide this whole circular ring in the in small current elements. We have to divide it into that small elements, ring elements of length dl, like this, dl, 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 like this. And for each element we'll try to calculate the electric field, small amount of electric field d, and then we will integrate it like that. So the final expression is like this. Okay, qx by 4 pi epsilon 0 r square plus x square to the power 3 by 2. This is the electric field due to a circular ring. You can remember the formula. This formula will come in handy in our discussion. Okay, so this is the electric field intensity at a point P at a distance x away from the center of the ring of radius r. This. Okay, electric field due to a circular ring. Next is electric field due to a line charge. So let us say we have a long wire of linear charge density lambda. Okay, long wire of linear charge density lambda. Linear charge density means lambda coulomb per meter. So this charge distributed uniformly at each unit length of lambda coulomb per meter. So it can be of any value. The value of lambda can be anything. Lambda can be 1 coulomb, lambda can be 2 coulomb per meter, like that. So let us say we have a total charge of 4 coulomb distributed uniformly over a wire of length is equal to 2 meters. So in that case, the linear charge density will be total charge by length, which is 4 coulomb by 2 meter, which is equal to 2 coulomb per meter. So like that. Okay, so that is the linear charge density. So here this long wire has a linear charge density of lambda coulomb per meter. So if we want to determine the electric field at a point P at a distance r away from the wire, perpendicular distance, so in that case that is given by lambda by 2 pi epsilon 0 r. Okay, so this is the electric field due to a line charge. Again, I am not going into the derivation thing, I am simply stating the formulas. Then we have electric field due to a spherical shell. Okay, so let us say we have a spherical shell of radius capital R. Okay, So there are three cases here. First, if we want to calculate the electric field at any point outside the shell, okay, which is away from the surface of the cell at a certain distance. So this is one case. Then another case is the electric field on the surface of the cell, okay, that is the second case. And another case is somewhere inside the shell, okay. So these three cases are there. So for the first case, where the point is at a distance away from the surface of the cell, so it is at a distance small r from the center. So in that case, the electric field intensity will be given by Q by 4 pi epsilon 0 r square, where the spherical shell carries a charge Q, okay. The total charge carried by the spherical shell is Q, okay, Q by 4 pi epsilon 0 r square. This is outside the surface of the shell. On the surface of the shell, okay, for a point on the surface of the shell, that is the second case, the electric field will be given by sigma by epsilon 0. So here sigma is the surface charge density. Like we had linear charge density lambda, we have surface charge density sigma. So it has a unit of coulomb per meter square. Okay, so let us say we have a total charge of 16 coulomb, okay, distributed uniformly over an area of 4 meters square. So the surface charge density will be given by Qt by A, which is equal to 16 coulomb by 4 meters square, which is equal to 4 coulomb per meter square. So like that, okay. So here the entire charge Q is distributed uniformly over the surface area 4 pi r square. And the third case is when the point is inside the shell, the electric field intensity is equal to 0, okay. So this is electric field intensity due to a spherical shell. Then we have is electric field intensity due to a plane sheet of charge. So here again we have a plane sheet of charge where positive charge is distributed uniformly, and we want to determine the electric field at a point P at a perpendicular distance r from a certain point. So in that case, the electric field is given by sigma by 2 pi epsilon 0. Again, sigma is the surface charge density of this plane sheet of charge. Okay, so since we have discussed, taken this discussion related to linear surface and volume charge density, let us just elaborate on that. So linear charge distribution, again, let us say we have a rod or a wire something which has a linear charge density of lambda, okay, lambda coulomb per meter. This is the linear charge density. So in that case, the electric field at any point P at a distance r from a small element dl is given by 1 by 4 pi epsilon 0 integrating this whole charge, okay, dividing it into small elements dl, okay, dl, dl, dl like this, and then we get the total length dl, okay, L, and then we multiply it with the linear charge density. So it's the same thing, integration of lambda dl. So that gives us the total charge of this wire or rod of length L. So this gives us this whole thing, that is the total charge distributed over this length. So this becomes the electric field at a point P at a distance r is given by 1 by 4 pi epsilon 0 integration of lambda dl by r square. This is the total charge distributed over the entire length. Similarly, for a sheet of surface charge density sigma coulomb per meter square or anything, whatever unit is used, in that case the electric field at a point P at a distance r away from a small surface element ds. Here we divide this entire thing into small surface elements and then we integrate the whole thing. Okay, so here we have taken a small surface element ds, then considering that we have integrated it to get the whole surface area, and then we multiply the surface charge density to get the total charge distributed over the entire sheet. So that gives us 1 by 4 pi epsilon 0 integration of sigma ds by r square. This gives us the total charge distributed over the entire sheet. Okay, similarly volume charge distribution, let us say we have a three-dimensional volume with volume charge density rho coulomb per meter cube. So here we take a small volume dB and we have to determine the electric field intensity at a point P at a distance r away from the small element. So for that we divide this into small volumes like this. Okay, small volumes like this, and we integrate them to get the total volume, and then we multiply the volume charge density to get the total charge QV. So this integration, this gives us the total charge distributed in this entire volume. So that becomes EP is equal to 1 by 4 pi epsilon 0 QV by r square. Okay, next is electric flux. So electric flux at any point through a given imaginary area in an electric field is the total number of electric field lines passing through that area. So it is simply the dot product of the electric field intensity and the area vector, which is radially outwards directed perpendicular to the surface of the imaginary area. So this is EA cos theta, the electric flux. Okay, the electric flux is simply the dot product of the electric field intensity and the area vector of the imaginary area. Next is Gauss law of electrostatics. So Gauss law of electrostatics, it states that the total electric flux passing through any closed surface, okay, any closed surface or area A, is 1 by epsilon 0 times the net charge enclosed by that surface. So here if we take this example, so here let us say the total charge enclosed by this whole imaginary area is QT, let's say QT. So in that case QT or QNet, let's say QNet it is, total charge is QNet. So this QNet can be anything. Suppose there are three charges, plus Q1, plus Q2 and minus Q3. Three charges, two are positive, one is negative, so this is the net charge. So in that case, this is the closed area. The electric flux phi, which is the same as the dot product of the electric field and the area vector, that will be equal to Q net by epsilon 0, 1 by epsilon 0 times the net charge enclosed by that surface. Okay, so this is the thing. There are two definitions or two ways in which we can determine the electric flux. First, through the dot product of the electric field and area vector. And the second one, if we have the net charge, then we can also determine it through this way, 1 by epsilon 0 times the net charge. So this is the closed surface, closed area, and here there are three charges, plus Q1, plus Q2 and minus Q3 here. So net charge is this much. So if we want to determine the electric flux, we simply do 1 by epsilon 0 times into plus Q1 plus Q2 minus Q3, which is the net charge, and we'll get the result. So here are some of the basic concepts related to electric field, Coulomb's law, electric flux and electric field intensity due to various conductors, which might come into play in our discussion related to transmission line conductors. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you.